Welcome to our lecture on running a simulation study. We've already had a lecture on Monte Carlo simulation basics, from which you may recall the general recipe for Monte Carlo, which is first to write a function that carries out some kind of random experiment once, then to use iteration to call that function a large number of times, and then to store and summarize the results, making sure to set the seed for replicability. Today, we're going to look at some more complicated examples that call for a more complicated recipe and some more powerful tools. At the end of this lecture, you'll know what you need to know to implement much more interesting simulation studies of the kind that you might need to use in your research. We've already encountered the function map from the purr package. Today we're going to learn a bit more about it, but as usual, I'm only going to be able to scratch the surface of this topic, so I'd strongly encourage you to learn more. You can consult the purr cheat sheet, the purr tutorial, and also some chapters from the books I've mentioned in earlier lectures, R for Data Science and Advanced R, both of which are freely available online. Let's start off with the basics. What is a functional? Purr is all about functionals, and a function is, I should say, a functional is a function that either takes another function as an input or returns another function as its output. A key example is the map function from the purr package. So what map does, in short, is if you've got a list of elements, x1, x2, up through xn, and you've got a function f, then map returns a list containing f of x1, f of x2, all the way up to f of xn. So in essence, this replaces a for loop. It's the first argument to map is either a list or a vector, and the second is a function. The output is exactly identical to that of this for loop at the bottom of the slide, but the nice thing about map is that we don't actually have to write the for loop. We don't have to set up an empty list, we don't have to fill it, we don't have to check the indices, and we don't have to use any kind of subsetting with brackets. So it's much more convenient. Here's a little example. I've written a function that takes in a vector and returns another vector that with two elements, the first of which is the sum of all the elements of the input vector, and the second of which is the product of all the elements in the input vector. Now I'm going to test it out on a list x that contains three vectors, 1, 1, 1, 1, 2, 3, and 3, 3, 3. I will load the tidyverse, which includes purr, and then I will use map to iterate over the list x and apply the function sumProd to each vector in the list. The result is another list. So the first element in the list is the vector 3, 1. The second is 6, 6, and the third is 9, 27, which correspond to the sums and products of each of the three vectors in the input list. Now, sometimes we may want to output something besides a list, and there are a couple of different ways to do this that we're going to talk about. One that is convenient in situations like the one on this slide is to use the functions mapdfc and mapdfr from purr. Now, full disclosure, these two functions are superseded. That means that they're still going to be inside of purr. They're not going to go away, and they're still going to receive bug fixes and updates of this kind. But for some philosophical reasons, the developers of purr feel like these functions don't quite meet their rigorous standards of sort of like purr, what should we call it, authenticity. So in some sense, they behave in ways that are somewhat different from some of the other purr functions, and they feel like that kind of inconsistency could turn out to be confusing. So the suggestion is not to use these. I think that might be overkill. These are really quite handy, and they're particularly handy in the settings that we're going to use today. So don't be afraid of them, but if you want to understand what the philosophical reasons for why these have been superseded are, you can take a look at the purr documentation. So with all that throat clearing out of the way, what mapdfc does is it very conveniently binds the columns of a list and returns a data frame. whereas map_dfr binds the rows and returns a data frame. So in other words, whereas map on the previous slide returned a list with all of those separate vectors, these alternatives kind of compress that list into a data frame, which can be very convenient. So probably in this example, we like the one at the bottom best, map_dfr, because what that's going to do is preserve these column names. So we end up with something that is quite convenient and that it contains exactly the same information as the list, but in a more kind of compact package. So I should mention that the alternatives, if you don't want to use map_dfc and map_dfr, the alternatives that you need to look into are to take map and to combine it with the functions list_rbind and list_cbind. So you can take a look at those in the per documentation. The reason I'm not using them here is because they just make things a little more complex. And for the purposes of this lecture, I want to focus on the essentials. So I'll be using map_dfr later in this lecture. And as you'll see, it comes in handy. As I mentioned before, the first argument of map from per can indeed be a vector, in which case that vector is just interpreted as though it were a list. So then we're still returning a list. And if you don't like that, you could use map_dfc or map_dfr. There are many more friends of map. So these different friends refer to different special use cases. So for example, map double is a special case in which the function .f returns a scalar. Now my example from before did not. My example from before returned a vector. So the function map_double is for the special case where the function f returns a scalar, and the output of this function is going to be an atomic vector with the same length as .x. So this function is what is called type safe. So you know for sure that it's going to return an atomic vector of doubles, numeric values. And you know for sure that it's going to be exactly the same length as .x. There are other versions of the same idea, map_chr, map_int, and map_lgl, that are also type safe. So they are going to return character, integer, and logical respectively. Using these functions, I mean, in some sense, they're not really necessary. You could just use map, but these functions give you type safe behavior. So you can ensure that you're getting output that you expect. Using them is a form of defensive programming, which can be very helpful. These are kind of things we don't think about enough, I think, in research software development. But in industry, these are exactly the kinds of things that people worry about, because you want to make sure that you're getting the output you expect, particularly when that output is going to be fed into another function that is expecting a certain kind of input. So these can be quite handy in practice. And let me show you a couple examples. So these are silly examples, I should point out, because they basically kind of replicate R's underlying vectorized operations using this needless mapping. But nevertheless, they're going to show you how they work. So what I'm going to do here is, in the first example, I'm going to create an anonymous function, x², and I'm going to use map double to apply it to the numbers 1 to 10. And I end up with a vector of length 10 containing doubles, and they're equal to the squares of the inputs. I could do the same thing with map_int for this vector 5L, 10L, and so on. Remember that L is how we tell R that we want to have an integer rather than a double. Here my anonymous function is just taking x mod 3. So I'm looking at the remainder when x is divided by 3. So we're going to end up with 2, 1, 1, 1, 0. Now I've got a third example, map_chr. I'm going to take a vector that contains a very important message, and I am going to map that vector with the function toLower, which converts text to lowercase. Again, we're getting a vector of the same length as the input, and it has the desired type. And finally, a little example with map_lgl, and I've got an anonymous function here that just negates a logical element. Again, map isn't really needed, but they're just examples. Map2 extends the idea behind map to take not one, but two inputs. So here, .x and .y are going to be vectors or lists of the same length. So here I'm calling them length n. And then .f is a function that takes 2 arguments. So whereas map had a function that took a single argument, map2 has a function that takes 2 arguments. This will return a list by default. There are variants of this map2 DFR, map2 DFC, map2 DBL that are analogous to those from map. There's also pmap, which stands for parallel map. And the way that parallel map works is the first argument .l is either a list of lists or a list of vectors, namely a data frame. And .f is a function that takes r arguments. So at the top of this slide, I'm showing you the basic idea. I've got this sort of data frame type thing with columns and rows. And you see what happens is that the function f is applied to the first row. So the function f takes in L11, L12, all the way up to L1R, and I return the output of that. Then I do the same thing for the second row, L21, L22, L2R, and so on. This function returns a list by default, but again, there are variants that are analogous to the things that we've seen before. Okay, let's look at some examples to make this more concrete. Let's try map2. So map2 needs a function that takes 2 elements, and that function can have completely arbitrary argument names. So here I've written an anonymous function that takes 2 inputs, foo and bar. It simply raises foo to the power bar. So I'm going to feed it 2 vectors. .x will be 6 to 10. .y will be 1 to 5. So I am raising 6 to 10 to the power 1 to 5. Now again, this is a very silly thing to do. I could have just used R's built-in vectorized operations to do that. So this is not intended as an example of what you should do in practice. It's intended as an example of how the syntax of map2 works. All right, now the next thing I'm going to do is create a little data frame. So here we go. I'll use my tibble function. I've got 3 columns, col1, col2, col3. I've just put in some sort of arbitrary data, 1 to 5, 5 to 1, and -2 to 2. And now I will show you how we use pmap double. I'm going to make up, again, an anonymous function. What this function does is it's a function of 3 elements, but notice that the names actually need to match those of the input df. So that was not the case with map2, but it is the case here. So I'm writing a function that is going to look inside of that input df for those particular columns. So the argument names have to match, and then it's going to use them to carry out the calculation. So here what I'm doing is I'm taking the column number 3, and I'm dividing it by the square of the sum of columns 1 and 2. Again, this is very silly. You wouldn't need to do this in real life, but it's just to illustrate that pmap actually does require the argument names of the function to match the names of the input. So now is a great opportunity for you to practice what you've learned. Here's a code snippet from our earlier lecture. Using your newfound knowledge of PER, you can explain it, and sort of working in reverse, you could construct a for loop that replaces line 7. So as usual, take a moment or two to think about this, try your hand at the exercise, and then check your solutions against those on the course website. Now it's time to carry out a substantive simulation study. I've picked a simple but kind of classic example. In this example, we're going to look at 2 different estimators of the variance of a population. So what we'll do is we'll consider n IID draws from a normal distribution with mean mu and variance sigma squared. We'll look at 2 different estimators. S squared is what I'm calling the usual estimator of the population variance. So that estimator is 1 divided by n minus 1 times the sum from I equals 1 to n of xi minus the sample mean quantity squared. Whereas this second estimator, sigma hat squared, is the maximum likelihood estimator. It's exactly the same, except it divides by n minus 1 rather than n. Now, in practice, that difference is not so substantial, and it's rarely going to really make any difference whatsoever in practice. But you may know that the reason why s squared is often preferred to sigma hat squared is that s squared is actually an unbiased estimator of sigma squared, whereas the MLE has a small bias. So the bias of the MLE is actually negative sigma squared over n. If this is a newsflash to you and you're curious how it works, at the bottom of the slide, I am going to give you a quick hint. There's a bit of algebra you need to do, then you take expectations, and you use the fact that these are IID. Now, this is not the world's most interesting example, granted, and it's an example where we already know the answer analytically. So why on earth would we do a simulation study? Well, because we know the right answer, we can check that our code actually works. And for the purpose of teaching you how to run a simulation, that's really valuable. But in spite of the simplicity of this example, it will turn out that it has all of the ingredients of the more kind of complicated simulation studies that you may want to carry out in real life for your research, or who knows, maybe in consulting or government or whatever other sort of walk of life you find yourself in. Here are the steps. First of all, we're going to write a function to generate simulation data. Second of all, we're going to write a function to calculate some estimates of something. Third, we're going to run the simulation for fixed parameter values. In other words, we're going to repeat two steps many, many times. The first step is drawing simulation data. The second step is calculating estimates. Then we're going to repeat this step 3 over a grid with a range of parameter values. And finally, we will store and summarize the results. So this is similar to the steps that we used in the basic Monte Carlo lecture, but now there are some extra elements. Notably, we're going to be considering different parameters that could have generated the data. So we want to evaluate how some estimator performs when the parameters might change. We're now going to step through every single one of the 5 elements from the previous slide in this little example with the bias of the maximum likelihood estimator. So step 1 is a function to generate simulation data. Here it is. I'm just going to use R norm n, and I'm going to set the standard deviation equal to s underscore sq. This is pretty simple. I just want to note that I'm actually taking mu equal to 0 in the simulation. The reason I'm doing that is that it doesn't make any difference to the results, and it just slightly simplifies the implementation. But the way I've written this function is to allow n and s squared to vary. So I'm allowing the number of draws from the population and the population variance to vary because I'm leaving those as arguments of the function. This is going to be important later on because those will be the 2 parameters that we want to allow to change and see how that impacts the simulation. In particular, what we want to see is how is the bias affected by n and s squared. And in order to allow this, we need a function that can draw simulation data for different combinations of these parameters. Step 1 was very straightforward. Step 2 is also pretty straightforward. So here I am writing a function called getEstimates. This function is going to return the 2 estimates, the usual estimator, which is just the sample variance, and the MLE, which divides by n, not by n minus 1. Now here I am returning a vector. If you don't like that, you could have returned a list, you could have returned a data frame. This is just a bit simpler, and I am going to be binding the rows later on with mapdfr, so this is sort of convenient. This is a little aside, but sometimes there are estimators that could fail to exist for certain data sets. So what would be an example of this? Well, you might have to think a little bit hard, but if you think about, for example, let's suppose you have an instrumental variables estimator. So the instrumental variables estimator is going to require that there is some correlation between the instrument and the endogenous regressor. If you had a really, really small sample size, it is possible that in the sample, that correlation could potentially be zero, in which case the estimator wouldn't exist. Now, it's very unlikely, but it could happen. There are other situations where an estimator could fail for similar sorts of reasons. There's some division by zero, or you're trying to solve for the root of a polynomial, but actually it doesn't have a root. So if you're in a situation where that could happen, and there's some non-negligible chance of it happening, you may want a way for your simulation to fail gracefully rather than just crashing midway through. So if you find yourself in that situation, the function possibly can be very helpful. This is also from Per. What it does is it suppresses the errors and it stores a designated value in case of failure. So I'd like to show you how this works by creating a funny little vector here, or rather I should say list. So my list is x, and it has 3 elements. First is core ERM, next is 3, and the next is 4. Lists can store heterogeneous types, so there's nothing wrong with this. I've got character, and then I've got numeric data. So now let's try to use map double. So I'm going to map double x comma log. So I'm taking the natural logarithm of all of the elements of this list, and it fails. Notice how it fails. It doesn't give me the log of 3 and the log of 4. It doesn't give me anything because it has hit an error on the first try. And this is pretty irritating because, maybe you would like to know the log of 3 and the log of 4. What possibly allows us to do is allows us to specify what should happen if the function that we're mapping fails. So if we change the code from line 2 above and replace that log with possibly log, comma, na underscore real underscore, that tells R, hey R, try to take the logarithm. If for whatever reason you can't, what I would like you to do is instead record an na. And just by the way, R, this na should be a numeric na. And we try this out on our little example. And now, rather than giving up at the first time it encounters an error, R instead says, can't do it. I'll put in an NA, and then it keeps going. So possibly can be very, very convenient in practice. Okay. So the third step, now that we're done with that aside, is to run the simulation for fixed parameters. So we're talking about the 5 steps here of the simulation. We're now on number 3. So the way I'm going to do this is I'm going to first generate a large number of simulation data sets. So what is a large number? Well, for the moment, let's do 3. Just 3 to illustrate the idea. So what I will do is I will use the code from our Monte Carlo lecture, where remember we used map, and then we had an anonymous function of I. You can see in line 3, after I set the seed, what I'm doing is I'm using map, and I'm using my function draw sim data. So I chose to draw simulation data with a sample size of 5 and with a true population variance of 1. And by using map 1 to 3 with this anonymous function of I, notice that draw sim data is not a function of I. So this is a trick, it's a very convenient trick, that is equivalent to just running that function over and over a certain number of times. How many times? Well, it's 3. Okay, so what do we get? We get a list. Each list is one call to the function draw sim data with the arguments n equals 5 and s squared equals 1. So each of these list elements is a vector of size 5. And if you recall how we generated the simulation data, if you recall what the draw sim data function does, it's actually making 5 normal draws with a mean of 0. I should say when we specify n is 5, it's making 5 normal draws with a mean of 0. And when we specify s squared as 1, those are all going to have a variance of 1. Why do we get 3 of them? Well, that's what map is doing for us. And the reason that we want to do this is because we want to calculate the usual and maximum likelihood estimators on several data sets. So how do we do that? Well, one convenient way to do it is to use mapdfr. So I'm going to map over those simulation data sets using the function getEstimates. and that returns a tibble, 3 by 2. So 3 because we had 3 data sets, and 2 because we had 2 estimators. Each row gives me the estimators from the corresponding data set above. So in the first data set, which you can see negative 0.5, negative 0.87, and so on, the usual variance estimator is 1.47, whereas the MLE is 1.18, and so on. All right, now 3 is not really very many, and the whole point of a simulation study is to repeat some random experiment enough times that the law of large numbers kicks in, and we can approximate some quantity that we maybe don't have analytical traction on, or that we don't know how to derive an exact answer for. So what's a big number? Well, if it's not 3, then maybe, how about 5,000? So what I'm going to do now, it's exactly the same as before, except now my sim datasets list will have 5,000 elements. So we'll have 5,000 datasets. Each of them is of size 5 because I passed the argument n equals 5 to the function draw sim data inside of that map command in line 3. Then I will get the sim estimates by using mapdfr. And again, if you don't like the fact that mapdfr is superseded, you can go read up on that, but it's very convenient for this example for me to use it. So now I'm going to end up with another tibble, and it has 5,000 rows. It has a row for each of the simulation data sets, and it has 2 columns. It has one for each of the 2 estimators. So we have, in some sense, we have done a full version of the simulation study. However, we've only done it for fixed values of the parameters. So we've only done it for n is 5 and s squared is 1. So we might also like to do it for other values of the parameters. What happens if n is 3 or 7? What happens if s squared is 5? Well, before we get there, we will get there, I want to talk about what we can do now that we have the results of the simulation for one set of parameter values. And the answer is we can approximate the bias. So let's remember what parameters we set in this particular example. We set n is 5 and s squared is 1. So I'll just hard code those values on the slide to make things simpler. Now what I will do is I will take my simulation estimates, which if you remember was a tibble with 5,000 rows and 2 columns, one for each of the estimators. Then I will compute the bias. What is the bias? Well, I'm going to compute the bias of the MLE, and I'm going to do it 2 ways. One way is I'm going to use the analytical bias formula, so I'm calling this bias underscore true. That's the thing that I showed you in an earlier slide that you can derive with a bit of algebra. So the bias of the MLE is exactly equal to minus s squared divided by n. So in this particular case, because this s squared is 1 and n is 5, the bias is minus 0.2. So now let's compare that to the bias that we calculate using bias underscore sim equals mean MLE minus s squared. What's happening? Well, we're taking the average value of the MLE relative to the truth. So we're taking the average distance, I should say the average difference between the MLE and the truth, which is precisely what bias is defined to be. And we get a result of minus 0.197. Not bad. It's very close to the correct answer. And if I had done more than 5,000 simulation replications, it would have been most likely even closer still, because the law of large numbers would be kicking in. So great. So now we've actually done one full run of the simulation. We've computed a useful result. And now we're going to expand. So the first thing we need to do to expand is we want to set up our parameter grid. So let's see how this works. Okay, to do this, the first thing I'll do is I will wrap my step 3 from above into a function. So and this is not actually anything new. So this is just exactly the same thing we had before, but now I'm going to wrap it inside of a function. So I've got a new function called runSim, and it takes 3 arguments: n, s squared, and n reps. And notice that I've given n reps a default argument of 5,000, so that by default the simulation will have 5,000 replications. What do I do here? Well, I do exactly what we did before. It's just I do it inside of a function. So I first simulate and generate all of my 5,000 data sets in line 2. Then I use mapdfr to get the estimates corresponding to each data set and store them in this nice tibble. So you will notice that if I set the seed and I run the simulation, I'm actually getting exactly the same thing as I did before, which isn't surprising. That's what setting the seed accomplishes. Okay, so far there's nothing new. But as I mentioned, we want to run the simulation over a grid of parameters. We're not just happy with n is 5 and s squared is 1. We want to try some alternatives because we want to see how the bias and other quantities vary as we change those parameter values. A really convenient way to set up your parameter grid is to use the function expand_grid from tidier. So here's how it works. Simparams gets expand_grid, and then we specify the grid values. So n is 3 to 5, and s_sq is 1 to 3. What this does is this creates a tibble with every possible combination of 3 to 5 and 1 to 3. So you see we've got a tibble here with 9 rows because we have 3 elements for n, and we have 3 elements for s squared. So we have 9 possible combinations, and they are all listed in that tibble, which I'm calling simparams. So what we now want to do is we now want to iterate over simparams. We want to carry out our simulation study for each of those combinations of sample size and true population variance. Okay, so how are we going to do this? Well, remember that when you want to map with more than one input argument, you have at your disposal map2, but that only works for 2 arguments. So if you want to map with more than 2 arguments, you use pmap. So we're going to use pmap here. Now you may say, but wait a minute, don't we only have 2 arguments? The answer is yes, but in general, and in situations that you may find yourself, you could have many more arguments. So I want to give you some code that's not so specific to the case where we just happen to have 2 different parameters that we're playing with. So we're only playing with n and s squared here, but in your simulation you may have many more. So in some sense, this is a much more general solution than a solution that would use map2. Nothing against map2, it's perfectly handy, but I just want to show you something that you'll be more likely to find applications for in your work. So what do? Well, it's actually very simple. We have a function runSim, and runSim has a default argument for the number of replications, but then it has 2 other arguments that happen to exactly match the names of the columns of simparams. That's not an accident. I set it up that way so that I can use pmap. Let me say that one more time because it's so important. I set up the tibble simparams to have columns whose names exactly matched the arguments of runSim. So remember, the arguments of runSim were n and s_sq. Those are exactly the same as the columns of simparams. So what pmap will do is it will match those columns up with the arguments of runSim. So what happens here? Well, we're going to produce a list. The list will have 9 elements, and I think I can scroll here to show you those. So as I go down, you see I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 elements. Each of these is a tibble with 5,000 rows and 2 columns. It corresponds to the 5,000 estimates that come from doing 5,000 replications of the simulation study at a particular value of the parameters. So each of these 9 list elements corresponds to one of the 9 rows in the tibble simparams. So the first row had a certain sample size and a certain value for s squared. So we're running the simulation at that sample size and that value for the population variance, and we're returning our 5,000 estimates because we did the simulation 5,000 times at those parameter values. So we have 5,000 values for usual and 5,000 for MLE. But we then move along to the second row of simparams. So now we're doing the simulation again, another 5,000 times, but we're doing it with a different value of n, the sample size, and a different value of s squared. And just because I think this can be confusing for people who are new to simulation, you have to keep in a track of the difference between 5,000, which is the number of simulation replications, and n, which is the sample size of each data set that we're using to do our to calculate our sample variance and our MLE. So we do 5,000 replications, but each of those replications has a sample size of, say, 5 or 3, depending on which row of simparams we are looking at. And again, because there are 9 rows of simparams, each of which corresponds to a particular pair of values for the sample size and the population variance, when we apply PMAP, we're going to get a list with 9 elements. Each of them is a tibble with 5,000 rows and 2 columns. All right, now we are done. So we have everything that we need, and we're going to summarize the results. There are many different ways that you could do this. I'm just going to show you some examples. This may vary in your particular use case, but quite often you might be interested in the bias, the variance, the root mean squared error of some estimators, and that's what I'm going to be looking at on this slide and the next. So the first thing that I'm doing at the top of the slide is writing a function called getSummaryStats. This function takes in a data frame, and it uses some dplyr commands that you should be familiar with to compute the summary statistics of the columns of that data frame. So this data frame is assumed to have columns usual and MLE, and it's computing the mean and the variance of those columns. So what this function getSummaryStats does is it processes one of the elements of the list that we saw on the last slide. So remember, on the last slide, we had a list of 9 tibbles. Each one corresponded to a parameter configuration. So each of those tibbles has 5,000 rows, and that tibble with 5,000 rows has 2 columns, usual and MLE. So what I've got here is a function that I can apply to that tibble to compute the means and variances of those columns. So now, once again, I can use the map DFR, which is very handy. I can take my simulation results, so this is in line 9, and I can pipe them into map DFR using the function getSummaryStats. So what I do here is I go through my list from the previous slide. I'm actually going to go back to it so you can see. So I'm going to iterate over this list of 9 tibbles. I go to the first one, and I compute the summary statistics for this tibble. So I'm computing the mean of this usual column, the mean of this MLE column, and then the variance of each of those. So I'm going to end up with a single row of summary statistics for each of these 9 tibbles. So I do it to the first one, then the second one, then the third one, then the fourth one, and so on. So that's what this first chunk of code does. Then I'm going to pipe this into bindCols simparams, because what I'm doing is I'm now going to attach the columns of the sim parameters to my results so that I know which set of results corresponds to which set of simulation parameters. If we go back just for a moment to the previous slide, you will see that the 9 tibbles inside this list of sim results, they don't have any sort of name that indicates which is which. But what we know is that they correspond to the rows of simparams, because that's how PMAP works. So this first one corresponds to the first row of simparams, and this last one corresponds to the last row. So all that we need to do now that we've summarized each of these big tibbles down into a single row, so we've taken the big tibble and we've computed the means and variances of each column to compress it into a single row. Now we're going to attach to it the values of the parameters that were used to compute the results for that particular tibble. And that's exactly what you can see down here. So we have these columns n and s underscore squared. We have them joined together with the variance and the mean of each of those 2 estimators. And now we're all done. So on this final slide, I am just going to compute a few more summary statistics. So in particular, I'm going to compute the MLE bias, which is the exact bias of the MLE that we can compute using some algebra and some basic statistics and probability. And then I'm going to compute the bias from the simulation study. So this is the bias that we get from our simulation without necessarily needing to know the formula. So if our simulation is set up correctly, the analytical bias formula in the column MLE underscore bias should give us a result that is very, 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 very close to MLE sim bias. So again, you might ask, well, why are we doing this exercise? We already know the answer. And the point is, I want to show you that the simulation actually is working as expected. So in your real work, in a real simulation study, you probably wouldn't have that first column. You wouldn't have that analytical solution. But I'm showing it to you so that you can see that the bias we computed by simulation is correct. And the way we get the bias is we look at the mean of the MLE and we subtract the true parameter value. How do we know the true parameter value? Well, it's a simulation. So we set that value. We, in fact, connected it to the results on the previous slide when we did that, that binding of the column in. And now I'm going to calculate this bias of the other estimator, the usual bias, and then I'm going to compute the root mean squared error of each. So what is interesting to see here, you might find this surprising, is that the MLE is biased, but actually the MLE can have, in some cases, it can actually have a superior root mean squared error. So it can actually have a lower root mean squared error. And that is an example of what is called the bias variance trade-off. So in many interesting problems in statistics, if you want to attain a lower bias, you may do so at the cost of a higher variance. So this is actually one example of that. That is, so even though this example is very simple, there's still maybe some surprises in store when you do a simulation study. All right, now that was a lot. And if this is the first time that you've ever thought about a simulation study in detail, you may have found that kind of difficult to keep track of. So this is my attempt to make things a little bit clearer. And for some reason, this doesn't display quite as beautifully when I go to full screen as it did when I was not in full screen, but I hope you can still see it and read it. I think everything should still be pretty clear to see. So I would like you to start by looking at the orange boxes on this flowchart. So the orange one, starting at the top, we set up a parameter grid. And that parameter grid had 9 different combinations of parameters. So we started off with n is 3 and s squared was 1. And we had lots of other combinations until we got all the way over to the very right-hand side, the orange box. N is 5 and s squared is 3. All right, so we had all these parameter values on the grid. What happens next? Well, on the top left, if you look at the green boxes, we're now going to generate 5,000 simulated data sets. And these data sets each have 3 observations. Why? Because that particular point on the parameter grid corresponds to n is 3. It also corresponds to s squared is 1. So we generate these 5,000 data sets. Then for each of them, we're going to calculate the usual estimator and the MLE. So those are the blue boxes. All right. So what are we going to do next? Well, now we're going to take all 5,000 of those estimates, and we're going to put them together into a table with 5,000 rows and 2 columns. So what is this? This is the full set of results for when n is 3 and s squared is 1. But we're going to do that for every single point in the parameter grid. So now we could go to the next point on the parameter grid, in the orange box at the top, and we could do exactly the same thing till we make our way all the way over to n equals 5 and s squared equals 3. Each time we end up with a table with 5,000 rows and 2 columns that contains the result for that particular combination of parameters. Finally, we feed these results in, so we had 9 of these tables with 5,000 rows and 2 columns to compute means, variances, bias, and so on. And finally, we put it all together. We take these statistics. So we have statistics that we've computed for each of the points in the parameter grid. We join them together with the parameters themselves so we can see which they correspond to, and we make a final table of results. All right, so that is a simulation study from top to bottom. But there are many different ways to run the same simulation study. There are many different ways to set them up. And these different approaches can all be perfectly valid, and if you do them right, they will all give you the same result, But there are some trade-offs, and the sorts of things that you can trade off are things like memory usage on your computer, how your code is organized, and how reusable your code will be. Now, there are many different ways that we could have done the simulation that I just showed you, but what I'd like to do now is maybe illustrate 3 fairly common approaches that you will see in practice. So I'm going to call them V1, V2, V3 to designate 3 different versions of the simulation. So V1 is the version that we just saw, the one that we've spent most of this lecture working through. This is a version that generates all of the data sets first and then calculates estimates. Version 2 is actually going to process one data set at a time, and then version 3 is going to do everything in line. So I will step through these in a moment, but I just want to clarify before I do, going back to the flowchart, that I am not going to be talking now about the orange part of the flowchart, and I'm not going to be talking about the yellow part of the flowchart. I'm going to be talking about the part, if you look in the top left, with the green and blue and purple boxes. I'm going to be talking about the part where we have fixed a location in the parameter grid. So I'm going to be talking about the part where, say, we've set n to 3 and s squared to 1. So, there are many different ways you can run a simulation, and even for this sub-part of the simulation, there are many different ways to set it up, and I will show you 3, one of which corresponds to what's on the flowchart. Okay, version 1 you've seen. So the code block on this slide is just copied from above. Here are the pros. It provides the kind of clearest conceptual separation of the different steps in the simulation. The advantage of this is that it can be much easier to debug. So you can basically debug these functions one at a time. You can test them separately. Because we generate all the data in one fell swoop, you could reuse exactly the same data sets with different estimators, even estimators that you haven't programmed yet. So if you wanted, using an approach like this one, where you generate all the data sets first, remember, in line 8, sim data sets, map 1 to n reps, I draw sim data, we generate all those data sets and store them, right? So we generate all of the 5,000 data sets in one go. We could store those and just hang on to them. We could write them to a file, and then we could read them in later. So this means that if you change your mind, you later want to try out a new estimator, well, the data's already there. This also makes it easy to parallelize separate steps of the process. In a later lecture, we're going to talk a bit about parallelization. But while in this particular simulation, it's actually trivial to draw those normal random variables that we need, in other situations, your simulation might be highly involved, and it might take a very long time to generate a single data set from your DGP. In that case, you may want to parallelize it, and the approach that we're using here would actually be amenable to parallelization. There'd be a couple of changes necessary, but generating all the data sets first and storing them, that can be easily parallelized. What are the cons? Well, one con is it tends to be higher in its memory use. So for this particular example, that barely matters because we were generating 5,000 replications of data sets of size, 3 or 5. But if your individual data sets that you're simulating were huge things, like some kind of, complex graph object with hundreds or thousands of nodes and needing to keep track of like an adjacency matrix or something like that, you could start to run out of memory pretty fast. So that brings us to version 2. What we could have done, but we did not, is we could have drawn one data set and then gotten the estimates for that data set. So you can see that on this slide, I've kind of modified the simulation so that we don't generate all 5,000 data sets. We just do one and then get the estimates and store only those. So this is much less intensive in terms of memory requirements because, imagine that your DGP involved storing this giant graph or this giant adjacency matrix. Well, maybe your estimators are still, scalars, or maybe your estimators are still very small vectors. If so, then an approach like this just doesn't use up anywhere near as much memory as trying to store all of those replication data sets all in one go. This approach still maintains the kind of some of the modularity that we worked with before, so you can see that its structure is still pretty similar to what we did in version 1. And so this, this can be a good approach in many circumstances. A downside is that we can't inspect this intermediate data, so we can't inspect the data sets from the individual replications. And that might be a downside if we wanted to debug this particular code. It could be harder. There's also a little bit less flexibility. So in a situation like this, we really can't necessarily parallelize in quite the same kind of way. But this is a perfectly valid approach, and this approach can work well. You just have to sort of think about how it's being set up and how it affects the other choices that you might need to make downstream of this choice. So it's a perfectly valid approach, and it can work extremely well, and it might be what you want to do. All right, here's version 3. Version 3 says, I don't want to write all these separate functions. I just want to do my simulation really easily. So this version 3 just packs everything into one function. So it just sticks everything inline. This can also be a totally valid approach. And honestly, if I was just writing this simulation study for my own use, I was trying to whip something out really quickly and just get a little bit of insight, this might be what I would write, because I can do it quickly. It's fast. There's not a lot of lines of code. It's low in memory use. There's very few function calls, and it does the job. The downside of this is that none of the components are reusable. So if you look back to the previous 2 versions, there were lots of functions that for example, to get the estimates, there were lots of functions that we could have reused in other studies or in other examples. Here, it's really just completely bespoke to this case, and there are no functions besides the one that runs the simulation itself. This also makes it much harder to test and debug. It's a lot less flexible. So is this a good choice? Well, for a very simple simulation study, this could be totally fine. But if you're doing something intricate and complicated, as the functions that you need to simulate your data get more complex, and as the functions that compute your estimators get more complex, this inline approach very quickly becomes a terrible idea. So this is totally fine for a quick proof of concept or something very, very simple. But in general, this is not really an approach that I would recommend for anything beyond the simplest of simulations. All right, so that was all a bit dull. Important, but dull. So now I would like to try to pique your interest by showing you an example that has led to some surprises in recent years. So you may have encountered the book Thinking Fast and Slow by Kahneman. And here's a quote from that book. Amos and his students cause to stir with their study of misperceptions of randomness in basketball. The, quote, fact that players occasionally acquire a hot hand is generally accepted by players, coaches, and fans. The inference is irresistible. A player sinks 3 or 4 baskets in a row, and you cannot help forming the casual judgment that this player is now hot, with a temporarily increased propensity to score. Players on both teams adapt to this judgment. Teammates are more likely to pass to the hot scorer, and the defense is more likely to double team. Analysis of thousands of sequences of shots led to a disappointing conclusion. There is no such thing as a hot hand in professional basketball, either in shooting from the field or scoring from the foul line. Of course, some players are more accurate than others, but the sequence of successes and missed shots satisfies all tests of randomness. The hot hand is entirely in the eye of the beholders, who are consistently too quick to perceive order and causality in randomness. The hot hand is a massive and widespread cognitive illusion. Well, sometimes even Nobel laureates get things wrong. There was a relatively recent paper in Econometrica that pointed out that everything that I just read you is incorrect. So in particular, this paper, Surprised by the Hot Hand Fallacy, a Truth in the Law of Small Numbers, found the following result. We prove that a subtle but substantial bias exists in a common measure of the conditional dependence of present outcomes on streaks of past outcomes in sequential data. The magnitude of this streak selection bias generally decreases as the sequence gets longer, but increases in streak length, and remains substantial for a range of sequence lengths often used in empirical work. We observe that the canonical study in the influential hot hand fallacy literature, along with replications, are vulnerable to the bias. Upon correcting for the bias, we find that the long-standing conclusions of the canonical study are reversed. Now, what is the lesson here? Well, It turns out that the subtle error, this very subtle but substantial bias in a common measure of conditional dependence, is so subtle that it was missed by dozens of extremely smart people, including Nobel laureates, over decades. But you could find it in 5 minutes by writing a simple simulation study. And so I ask you, why did none of the people in all of those years in this literature bother to try? That's a fascinating question about the sociology of science, and I don't know the answer. But I think that in some sense, simulation is viewed as, how could I say this, not such an exalted pursuit. Well, if you could really do the math, you wouldn't need the simulation. The simulation is only for unfortunate souls who just don't know enough measure theory and they can't do the probability calculations themselves. But my advice to you is that simulation is actually an unbelievably powerful tool, and it's arguably much more powerful than derivation. It can help us to learn things that would be impossible to do by hand. It can also help us to get some insight about problems that will later lead to us doing analytical calculations, and the two can be complementary. So my advice to you is, rather than trying to be clever and avoiding simulation because it seems a bit too plebeian, why not try to be right instead? It's unfortunate that it's so easy to make mistakes, but that's just the human condition. So let's build a robust set of tools that can help protect us from our own mistakes and lead us to making better conclusions. One of the best tools that I know of is simulation. So if you're watching this lecture at home, well, I hope you'll be joining us in Core ERM for our class meeting that's coming up soon, because we're going to look at this particular example in some detail. And now I would like to tell you a little bit about how this is going to go. The full details will appear on the course website. You can go down the schedule of lectures to find this lecture, and you'll see the hot hand example linked from there. We're going to be looking at a vector called shots, which is a vector of zeros and ones. These are the shots made by a basketball player. A hot hand is a situation where a 1 becomes more likely after we've seen a streak of ones, so a sequence of all ones in a row. Now, before this Miller and Sanjudro paper, here is how researchers looked for a hot hand. They started by identifying each streak in the vector, shots, which is a sequence of k ones in a row. And then for each streak, they looked for the shot that immediately follows it. Then you could collect these into a vector called aftershots. And the hot hand would mean that the mean of afterstreak is bigger than the mean of shots. And an IID sequence should say that the mean of afterstreak is approximately equal to the mean of shots. That was the idea. That's the test that researchers used. So, as we now know, this approach is flawed. And in the exercise, what you will do is design a simulation study to show this. And I hope you will reflect on the importance of simulation in research. If you'd like to see a more readable explanation of the hot hand bias, much more readable, I would say, than the Econometrica paper, you can click on the link on this slide. As always, slides are linked from the course website, and it will take you to an article from the Journal of Economic Perspectives.